Pre-matriculants, welcome to This is Learn Extra Live, your favorite show, your best learning show ever, right here on 319. I am Abram, and I'm not alone. I'm with Tracy. How are you, Tracy?
Fine, and you?
Happy Women's Month, and I hope you enjoyed your Women's Day.
I was working, but thank you.
All right.
It's all right. I enjoyed it. You know, it was
Well,
just...
this is your month. Enjoy it.
Yeah, thank you.
All
Thank
right.
you.
And what are we doing today?
Today we're doing energy and chemical change. It's actually a really nice section, lots of little bits and pieces, but it's a lot of fun. I quite like this section. It's sort of a introduction to stuff for next year.
All
So
right,
it's
if
very
you
cool.
like it, so am I. So let's learn more and learn extra. My sisters, if you're joining us now, you're not late, you're just on time. Go over Facebook and like our page if you haven't. But if you have, make sure that you go to facebook.com/learn extra. Like our page, and let's get talking over the page. If you have any questions, and also if you need to help other mindsetters, that's what we are having Facebook for. Team mindset all the way. Let's help one another. Second thing that you need to know is that you can follow us on Twitter at LearnExtra. And lastly, download your notes all for free on learnextra.co.za/live. So let's get to it. Learn more, Learn Extra with Tracy.
Oh, thanks, Avram. Okay, well, guys, like I said earlier, we're doing energy and chemical change. This is the start of chemical change for you for this year. And we're going to cover quite a few things today, and it's going to look like a knot, but it's not actually. So what we're going to do is we're going to talk about the energy change in chemical reactions, okay, because that's quite important. We're going to define now exothermic and endothermic reactions. I know you know what they are because you've dealt with them along the way, but we're going to define them now. We're going to define a concept called bond energy, which hopefully you've actually come across before now, right at the beginning of the year, when you did bonding and you did molecules and you did shapes and you did bond length and all of that sort of stuff. We're going to define an important concept called activation energy and the activated complex. And then we're going to discuss potential energy diagrams. It sounds like a lot, but they actually all just work together, which is really nice. So we're going to jump right in there, and we're going to talk about what is an exothermic reaction. Now, I know you know this because you've done this since grade 8 already. Hopefully, you were using the term exothermic reaction. And remember that an exothermic reaction... Oh, no, that's not going to help me. I don't know what happened here. There we go. It's yellow now. So, really? Exothermic. I was told the pen works. Pen's not working. Okay, there we go. Let's try this again. Let's not do that. Let's use one of those. Okay, there we go. And sorry, that's my fault. I actually can't remember how to use the board. It's been so long.
Oh.
Anyway, exothermic reaction is a reaction where the system becomes hotter. So you burn magnesium in oxygen. Gives off a flame, gets hot, we're all okay with that. Heat is given to the surroundings, nice and easy. Now, a good example of that is when we burn fuel. Okay, this is the example here that I've got is methane. Okay, methane plus oxygen, which gives me carbon dioxide, water, and energy. Now, what's important here, grade 11s, is that I've put the energy as a product. Okay, it's not a chemical. Okay, I'm not saying that energy has become a substance. I'm saying that it is something that's given off. We usually experience this in the form of heat. Okay, now an endothermic reaction is a reaction in which the system becomes colder. These are a little more unusual. You don't do a lot of those at school level, but you can still deal with them. And now what we say is that heat is taken in from the surroundings. Okay, so it takes heat in. A good example, and the one I've got on the board here, is with photosynthesis. So for the life science students, you all have seen this before. Carbon dioxide plus water. Now watch what we do here is we add energy, okay, as one of the reactants. So instead of saying we give off energy, now I'm saying I need to take in energy and I need to put it into the system. Okay, and I just saw a little bit of a typo, so when you look at the notes, just take that out. I don't know what I was doing. Okay, another good example of an endothermic reaction is those disposable ice packs. You know, if you're an athlete or you're doing something and you hurt yourself and you know you've got to put ice if you twist your ankle, which I'm quite good at, just falling off stairs. You twist your ankle or your wrist or whatever, and you know you've got to put ice on it, and you can get those disposable ice packs. Now, what those ice packs are is you break the inside. There's a packet inside the ice pack, and then it goes cold, 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 cold. That's an endothermic reaction, okay, because now you're forcing chemicals to interact with each other and they get cold. Okay, you also know with those ice packs you can't keep them cold forever because eventually the reaction stops, okay? So exothermic reactions, reactions that give off heat; endothermic reactions, reactions that take in heat. Okay, but this whole talk about energy, we now need to give it a nice fancy name because we're doing science, okay? And that fancy name is enthalpy, okay? Enthalpy, which is given the symbol H. I actually don't know why it's called given the symbol H. I know it's confusing, but just deal with it, okay? Now, enthalpy is defined as the total amount of chemical potential energy in a system. Chemical potential energy is the energy that a system has because there are chemicals involved. Okay, we can make use of that chemical potential energy by causing a chemical reaction, which then results in heat. We can use it to cause a chemical reaction results in electrical energy. There's lots of things we can do with that chemical potential energy, okay? Enthalpy as it stands isn't that useful, but change in enthalpy is delta H. Now, when I talk about changing enthalpy, grade 11s, what we're referring to here is we're going, how does the energy of the system change? So when I look at how much energy I had when I started and how much energy I have when I'm finished, what's the difference? Okay, and do we then experience that difference as heat? Does it get hotter? Does it get colder? What exactly is going on? Okay, and now this is important. And whoops, before I forget, enthalpy is an energy, it's measuring energy, so we measure it generally in kilojoules per mole. Kilojoules, thousands of joules of energy at a time per mole. You know what a mole is, you've done it lots up to this point, you've probably just finished stoichiometry. So per mole of substance, okay, and we can do it per mole of reactant, per mole of product, however that works. So it has a unit, it's not a ratio, it's a unit. In an exothermic reaction, okay, delta H is negative. Now this doesn't always sound like such a hot idea, because now you're going, all right, hang on, wait, you just said to me that an exothermic reaction is a reaction where I give off heat. Cool. Then we said enthalpy is the amount of chemical potential energy we have. We're okay with that. But now I'm saying to you that if enthalpy, the change in enthalpy is negative, then it's exothermic. How does a negative give off heat? Just hold that question for me, grade 11s. I promise I'm going to get back to it, okay? Because I know that's what you're thinking. An endothermic reaction, delta H is now positive, okay? And now we're going to think, we go, okay, enthalpy is the energy of the system. An exothermic reaction gives off heat to the system. An endothermic reaction takes in. When the delta H is negative, what that means is the system is losing energy, negative. It's losing energy to the system. The reaction is losing energy to its surroundings. Endothermic delta H is positive because it's taking in extra energy from the surroundings. Okay? That's great, but how do we know we get in there? Okay, so keep all of that in the back of your mind. We're going to need it now. Now we need to talk about bond energy. You did bond energy earlier this year, okay? When you looked at bond length, you looked at intermolecular forces and all sorts of things, and one of the things you would have had to do was bond energy. Now, bond energy is defined as the energy which is absorbed when bonds are broken or released when new bonds are formed. Now, listen carefully. When I break the bonds in a molecule, I have to give it energy because we want to break something that's already existing, okay? When new bonds are formed, okay, so now I go from, okay, I'm breaking old bonds. Old bonds need to give in energy, but Why do atoms bond together? Atoms bond together because they want to get to a lower energy state. How do they get to a lower energy state? By giving off their energy. Okay? So, absorb energy when we break bonds, give off energy when we make bonds. Okay? Going to keep this in the back of our minds. That helps us work out change in enthalpy, and we've got a little equation here which will not be on the information sheet. Change in energy, which is delta H, my enthalpy, is equal to, this is sigma, that means total, the total energy absorbed when I'm breaking all the bonds, minus the total energy released. Okay? But where do we get those energies from? Well, grade 11s, you do not need to learn bond energies. Now, this is quite a comprehensive table that I have, okay, over here. Whoops. If I don't, just, what did I do? Okay, I don't know what I've done again. No, let's, it's time for me to go.
Well, Tracy, while you're trying to figure it out, it's just a welcoming back. It's a welcoming back.
I got it. I got it. Sorry, guys. You know what? That's what makes watching the show fun.
Yeah.
You know.
A live show.
Absolutely. Anyway, and it's just my fingers. So, guys, there's a whole table here of bond energies, which is kilojoules per mole. You do not need to learn these values. Please understand that. In a test or an exam, if you need to use these values, they have to be given to you. Probably what will happen is you'll be given quite a comprehensive table like this, but you'll only need to use some of it, okay? There's no ways you'll ever have to use all of them. And they're not going to just give you the ones you need, because that would just negate you having to figure it out. But this is kilojoule per mole, because that's what we're doing. So what this is saying to me is that if I break a hydrogen H2 bond, okay, I need 432 kilojoules per mole of hydrogen to put into the system to break the hydrogen away from each other. But the converse of that is that if I'm now going to make hydrogen, H2, I'm going to release 432 kilojoules of energy per mole made. Okay? That's what this table means. Now, you should have seen something like this before, because you would have spoken about things like bond length, bond order, for how bond energy changes, okay? But let's quickly look at a problem which will then help us decide on, okay, how do I use this in calculating if it's exothermic or endothermic, which is what this question says. It says calculate delta H for the following reaction. Is the reaction exothermic or endothermic? Okay, so what we're going to do is we need to go fine. I need to calculate how much energy is taken in. So over here, okay, over here, that's my energy that's absorbed. Okay, and yes, I can write as well. Over here, that's energy released. Okay, so I need to work out total amount of energy absorbed, total amount of energy released, and I'm going to minus them from each other. Okay? Now, do you know what I think, Abram?
Yes.
I'm going to get about halfway through this, and then we're going to need to take a break.
Mm-hmm.
So what I'm going to do, guys, is we're going to take a break, but while we in the break, this is what I want you to do. I want you to decide for me what bonds and how many need to be broken, and what bonds and how many are going to be made, because that's a very important decision before we can actually move on. So I think with that, I think they can take a break.
All right, mindsetters, help Tracy, and then we'll see after the break how did you help her, whether you're right or not. And let's continue on that note. Don't go anywhere. Welcome back, Mindsetters. Now, as much as you need to help Tracy, we also need your help as Mindset. We're looking to hire someone. If you know of anyone who could be interested in doing some grade 10 to grade 12 CAPS aligned content development, review, and video presentation, make sure that you go over mindset.co.za/learn/jobs, because we're looking for that someone. The closing date is the 26th of August. So, Tracy, let's continue.
Oh, great. Guys, seriously, if you have a good science teacher, please get them to do this. It's such a wonderful opportunity. Okay, so we're back, and I'm hoping you managed to do what I asked you to do. So let's just quickly get rid of my scribbles, and we're going to talk about what is actually happening. Now, the point here, grade 11s, is we need to be able to decide how much of everything we have. Okay, so we're going to start with the energy. Let me have a pen that works. Energy absorbed. Okay, so what we need to discuss is how many bonds need to be broken. So let's look at this carefully. What we have over here is we have a hydrogen fluoride bond, so it's HF, and there's two of them. The number in front is very, very important here, grade 11s. So we have two HF bonds, and now we go, well, we have a Cl2. We know that Cl bonds with Cl with single bonds, so we only have one chlorine-chlorine bond. Okay? Things like knowing that chlorine bonds to itself with single bonds is very important, grade 11s. It's those basic things that, even though we're not testing you specifically about bonding at this point, we still expect you to know it, okay? So you got to understand that everything gets put together. So let's go back to our table and see what we have there in terms of bond energy and that sort of thing. And hydrogen fluoride, HF, is 569. So I'm going to be using this one. And Cl is 243. Okay, I don't know these off my head, just so you know. I need to look them up. So let's go back here. Okay. Yes. There we go. All right, and we're back at the HF, and we said that was 569, and the chlorine was 243, which gives us 382 kilojoules per mole. Okay, so we're okay with that. 1,382, not a problem. That means that I need to put in 1,382 kilojoules of energy per every mole of reactant in order to break everything up into its atoms. Okay? Then, the reaction proceeds, and now we need to look at energy released, because we're making new bonds. So we go back up, and we say, fine. Ooh, there we go. 2 HCl bonds, 1 fluorine bond, okay? So, the page, there we go. Alright, 2 HCl bonds, okay, single bonds, we know that, plus 1 fluorine bond, okay? We go back to our table because this helps us decide what we've got, and we said, well, we've got 2 HCl bonds, so it's 431, 1 fluorine bond, which is 159. So we're going to go back, and obviously this is a little bit easier in an exam because you all have everything together, you know, and you don't have to swap through pages. So now we get 2 times 431 plus 159, and we get 1,021 kilojoules per mole. So, what is this information telling me, grade 11s? In order to break all the bonds, I needed 1,380 kilojoules of energy to go in. When the new bonds are made, I only give off 1,021 kilojoules. So actually, I'm taking in more than I'm giving off. That makes this endothermic. Okay, but now we need to prove it because they wanted us to actually prove it. So my change in energy, which is what they asked for, is going to be my total energy absorbed, okay, absorbed with a B, minus my total energy released. That little ZE thingy funny symbol over there, that's sigma, okay? You know that from maths. Okay, so that means I'm going to go 1,382 minus 1,021, and I get 360 kilojoules per mole. Now, earlier today, I said to you that if delta H is greater than 0, then it is an endothermic reaction. This is very endothermic, okay? So this reaction, because delta H is greater than 0, it's an let me take that off. Delta H greater than 0, it's an endothermic reaction. Okay, it's endothermic. It takes in energy from the system around it, from the surroundings. Okay, if this was reversed and we went the other way around, then it would be exothermic, because we would have ended up with a negative answer. Okay, so moving on. Now we get to some really, really, really important concepts. For a chemical reaction to take place, we at school level often only really discuss spontaneous reactions. So reactions that maybe I need to add a little bit of heat to get it going, but we don't need to keep adding heat, or if we do heat it, it's just to make it go a bit faster. But generally we don't do a lot of non-spontaneous reactions. So the whole concept of activation energy sometimes gets a little difficult to get in our heads. But what activation energy is simply the minimum amount of energy I have to put into the system in order for the chemical reaction to happen. So we can put a whole bunch of chemicals together, but just because they're there doesn't mean anything's going to happen. We need to make sure that they have sufficient energy. Okay, that sometimes that means we have to heat it up. Sometimes things happen on their own and you don't need to add anything to it. There's lots of reactions where we don't have to add heat, but that's just because they have a very small activation energy. Okay, so activation energy, when we look at this, for a reaction to happen between two substances, just what I've said to you, the minimum amount of energy, there is a minimum amount of energy for the reaction to take place. That minimum amount of energy is called the activation energy. Okay, it's the absolute minimum. If the particles do not have that amount of energy, they will not react, no matter what you do. Okay, you can stand on your face and go blue. It won't help. Okay, they must have that minimum amount of energy. You guys okay with that? So, but now what actually happens is, this is like pushing a big rock up a hill, okay? It takes energy to get up to the top of the hill. But you're now at the top of the hill, and now it's like, is the rock gonna fall forward, or is the rock gonna go back down? Okay? And at that point, when the rock gets to the top, it's a place called the activated complex. All the bonds get broken in the molecules, in the reactant. So all the bonds get broken, and now they all come together in a big smush. That's a nice scientific word. Okay, so they all come together, and now they're at a little bit of a halfway stage. But at this point, we get an activator complex. The activator complex is an unstable, temporary complex. You cannot take it out of the system. I can't go, oh, there's activated complex, and put it aside. It doesn't exist outside of the chemical reaction. When the activated complex gets made, the system now has a choice to make. Either the activated complex is going to keep going forward and it's going to make the reactant, so give off energy, or it's going to go back down and make make the products and give off energy, or it's going to go backwards and make the reactants again. Okay? Unstable. It's temporary. Okay? Now, so what we have over here is when the minimum energy has been absorbed, we form the activated complex. Very important, guys. It is a temporary, high energy, unstable state. It's almost like a halfway stage. Okay, so it's a little like, and I'm probably going to show my age here, like in The Matrix, in the second movie, I think it was, when Neo got stuck in the train station. Do you remember that? Have you seen it? Yeah. Okay, so you get stuck in the train station. That was like the activator complex. Because he could either go backwards, which he didn't really want to go, but he really needed to go forwards. But he couldn't stay there. It wasn't like he could take the train station with him. Okay, so that was like the activator. It's that temporary state. Please don't write that in your exams. Okay, your teachers will not understand. It's just an analogy. Okay, so it's a temporary high energy state. All right, now that gets us to our energy potential graphs. These are so useful and really, really help us. What I have here is the graph for an exothermic reaction, okay? Now, it's the reaction between hydrogen and oxygen to give us water. Hopefully, some of you may be seen this. I particularly like doing this in my classroom. Can't do it in the studio. I'll probably break something. But you fill a balloon with hydrogen, put it on a string, light the string burns, blows up the balloon. Oh, it's such a fun experience. Put a little bit of oxygen in the balloon at the same time, big noise. It's great. Okay, very, very, very exothermic, okay? That's why we use hydrogen as a fuel. Now, what this graph tells me, first of all, my y-axis is potential energy, kilojoules per mole. It's related to enthalpy, okay? We start with the reactants, and the reactants have energy because they exist, okay? The reactants have energy just because they exist. Otherwise, none of us would exist, okay? They just have energy because they're there. Those reactants now need to absorb in energy, which is what we've just calculated with the last question. They absorb in energy in order to break. So we need to break up the hydrogen and the oxygen, and the way we do that is we absorb energy. So now the energy in the system gets bigger until we reach the peak. This difference in energy over here is the activation energy. That's the minimum. If I add in more than that, the reaction will go faster. If I don't add in enough, the reaction won't happen. So that's the minimum. At this point, we get the activator complex. This doesn't have a formula, grade 11s. You can't tell me it's H2O2 because that's hydrogen peroxide. You can't say it's HO because there is no formula to this. Okay? It's simply all those atoms bonded together while near each other, and this gives this complex. At this point, now new bonds need to be formed. So we've taken in energy to break bonds. Now new bonds need to be formed. When bonds are formed, we release energy. So that it goes from a place of lots of energy, loses this energy, and goes to a place of less energy. Okay? We've now formed the product. By forming the product, new bonds were formed, we gave away energy. The difference between here and here is delta H. That's my change in enthalpy. Okay, the difference in energy between my reactants and my products is my enthalpy. My reactants is a big number, products is a small number, and I'm going to go, we go products, I take the product's energy minus the reactant's energy, and I'm going to get a negative answer. Okay, so here, delta H is going to be equal to the energy of the products minus the energy of the reactants. And I'm going to get a negative answer. Okay? The label for the x-axis, grade 11s, this has there's lots of ways to label it except for one. Course of the reaction is acceptable. Reaction coordinate is acceptable. Reaction progress is acceptable. Time is not. Okay? You cannot put time on this axis ever. I know some textbooks do. You may not do that. Okay? So in exothermic reaction, products have less energy than the reactants. And I think, Auburn, It's time for a break, and then we'll do endothermic.
Well, it is. You know, talking about time, you're reminding me of a quote by Harvey Mackay.
Yes?
He says, time is for free, but it is totally priceless, because everyone can use it, but no one owns it. So
That's
time
brilliant.
is not ours.
I need to know where he gets these from. Because you were doing all the Nelson Mandela quotes last time too. I remember this.
I'll give you my secret after the break.
Yeah, we'll chat.
Stay tuned.
Okay.
Mindsetters, don't move also. We'll see you after the break. Welcome back, pre-matriculants. Now the Curio is up and available, just waiting for you. Go to curio.co.za and fill in that assessment. Do not skip any question, because we'd like to help you to see whether you understand or whether you still need some help. So it is curio.co.za. Your code is PS11. You can also log in to Curio via your Mixit. Add that as a contact, Curio. Thank you, Tracy.
Excellent. Well, that just came out of nowhere. Okay, so before the break, we said we take enthalpy. Change in enthalpy is energy of the products minus energy of the reactants, and with an exothermic reaction, the products have less energy when we're finished. So, if an exothermic reaction gives off heat and an endothermic reaction takes in heat, so it's the opposite. If we look at the graphs and we go, well, an exothermic graph means that the products have less energy than the reactants, then an endothermic graph must mean the opposite. Okay, so if we look at the endothermic graph, okay, the same thing. Now, it's a different reaction, okay? Please note, this is not carbon dioxide and carbon monoxide. It's a different reaction, okay? I can't use water, hydrogen, and oxygen again, because that is an exothermic reaction. I can't change that to an endothermic reaction. But the same concepts are happening. So we have our potential energy on the y-axis. We have course of reaction, which I said to you earlier can also be reaction coordinate or reaction progress, but cannot be time. Now, the reason why it can't be time, now I've been explaining it one way and I got told a much better way today, so it's actually really good, is if your x-axis is your x-axis is time, that would be 0 time. At 0 time, we have particles inside that system which has a certain amount of energy. If this is a time graph, then what this graph is telling me is that at every moment in time, every particle has exactly the same amount of energy, which is not what happens. Okay? When we look at the temperature of a system, we're looking at the average kinetic energy that the particles have. So we can't actually do this by time, because then the graph would be all over the place. So we can't use time, because not all the particles are doing exactly the same thing at exactly the same time. Okay? Because it's random. Remember that in a chemical reaction, grade 11s, you're actually looking at a reaction where you have millions of atoms and molecules and compounds bashing into each other at the same time. You cannot predict, essentially, what each of them are going to be doing at a specific point in time. Okay, so if we now look at this and we go, let's go back to what it's telling me. My reactants have a certain amount of energy because they exist. They have to take in energy till they get to the activated complex. The energy that they take in is the activation energy. So activation energy is still the difference in energy between where the reactants are and where the activated complex is. Okay, so if I know those values, I can work it out. Then the activated complex is happy to move forward, moves on to the forward reaction. So now we get our products, and the products give off energy as they get to the end, but they end up with more energy. So if you look at this, they end up, and that's just not a straight line, but just pretend, this is my product's energy over here, and this is my reactant's energy, and my reactants now have more energy. So I have less energy. My products have more energy than the reactants did. That means the products took in energy from the outside, which is where the activation energy comes from. But when the new bonds were formed, this is like the calculation we did, less energy was given off than they took in. That also means that delta H, which is the difference between the energies, is now positive. Delta H is positive, okay? this is all nice, but you know what, honestly, as humans, we don't like things to go slowly. We like things to go fast. So we can use a very important thing called a catalyst. Now, a catalyst can increase the rate of a reaction without actually taking part in the reaction. Sometimes changes phase, but it doesn't actually take part. What a catalyst actually does is it lowers the activation energy. So if we look at our energy graph, okay, this is for a exothermic reaction. Now, whether it's an exothermic reaction or an endothermic reaction, it makes absolutely no difference. A catalyst does exactly the same thing. Here's my original activator complex. By adding in a catalyst, my activator complex is now over here. It's lower. Okay? A catalyst, it's fairly complicated chemistry, so we're not going to worry too much about it. But a catalyst helps the reactants get to that activator complex part where it needs to get. Once it gets there, then we can make the products, okay? So a catalyst makes the activation energy smaller, but it does not change delta H, okay? A catalyst does not change the change in enthalpy. That is constant. Because the reactants have a certain amount of energy, the product will have the same amount of energy regardless of how it got from reactant to product. That doesn't matter to the enthalpy. Okay? How we got there, whether we have a big hill or a little hill, doesn't make a difference as long as we get there. That's all that matters. Okay? So, that brings us to the fun part. Questions. Okay, so what we have here. During the process of cellular respiration, glucose is broken down to form carbon dioxide and water according to the following reaction. So we have C6H12 plus 6O2 goes to carbon dioxide and water. The reaction is catalyzed by enzymes. What they're saying to you is this is a reaction we creating carbon dioxide and water. Okay, this is what happens when we breathe, by the way, and break down, cellular respiration is when we change sugars into carbon dioxide and water, okay? Sounds like we're doing life science a little, but life science and science often cross over. Catalyzed means that we can speed up the reaction by using enzymes. We don't need to know what those enzymes are, we don't need to know their names, we don't need to know their functions or what they look like, or it's not biology, okay? It's just catalyzed. The change in potential energy during this reaction in the human body is illustrated by the graph. So we go, okay, let's see what they've given us. Note that this graph, instead of saying course of reaction, is called progress of reaction. Reaction progress, same thing, okay? My reactants, this is my activation energy, so they've labeled it nicely for me. There's delta H, there's my product. And looking at this, I realize that my products have less energy than my reactants. So straight away, I'm just going to make a note for myself that this is an exothermic reaction. Okay? We're okay with that. First thing they ask. Use the graph to answer the following questions. Okay, that makes sense. First part. Is the breakdown of glucose an endothermic or exothermic reaction? We've just answered that. Because I said to you, looking at it, that it's exothermic. Okay, you see I've written it over here. It's exothermic. Okay, why did it? Because now they ask you why. The energy of the products is less than the energy of the reactants. Okay, so it's an exothermic reaction. Why? Energy of the products less than the energy of the reactants. Fairly straightforward. Now they say, explain how the enzymes influence the rates of reaction. And now you're going, but we haven't discussed rates of reaction, Tracy. No, we haven't. But let's just talk about the enzyme is a catalyst. So what the enzyme is going to do, if we look at this reaction, is it's going to make my activator complex happen at a lower height. Okay? It makes the activation energy smaller. As soon as we make the activation energy smaller, we make it easier for the reaction to happen. If it's easier for the reaction to happen, the reaction will happen faster. That's the point of using a catalyst. You do get catalysts that decrease, they make it go slower, okay? But we're not worried about that at this point for school level. The point of putting a catalyst into a reaction is to increase the rate, to make it go faster. Now, in the human body, this is all done naturally with the enzymes, but in industry, why do we need a chemical reaction to go faster? We want more product. If we get more product at a faster rate, we make more money, okay? Because that's pretty much why we do anything in industry, is to make money, is to help the economy. So that's quite important for us. So when it asks you, so the question said, okay, let's get back there, explain how the enzymes influence the rate. They don't just say, how does it explain? So we'd say, the enzymes increase the rate of the reaction by decreasing the activation energy. Okay? How? They increase the rate of reaction, they decrease the activation energy. Okay? We got that? All right. We have time for another question. Okay. I like this one. In the following energy profile diagram, guys, I've used a lot of words. I need different names for these things, and you need to get used to it. It's the same thing. It's the energy potential diagram. Okay? The x-axis represents the extent of the reaction or the reaction progress. The y-axis represents the energy of the reactants or the product. So we go, well, it's okay. If we look at it, it looks a little different because this was obviously drawn on a computer. And we go, well, they've given us values, which is always interesting. Minus 150, 100, 600. Don't worry about the fact that you got minus 150 above the line. It's in past exam paper, so don't stress about that. And we go, okay, high energy, low energy, it is a exothermic reaction. Okay, exothermic reaction. And we go, well, that's obviously where the reactants are, where A and B is, C and D is my products. I don't know what A and B is, and C and D, it doesn't matter. It's a general reaction that could be anything, okay? And they tell me over here that it's a reversible reaction. At this point, that's not that important, grade 11s, but what it does mean is it actually gives us the ability to read the graph backwards if we wanted to, okay? So if we're going from A plus B to C plus D, it's exothermic, okay? Because the products end up with less energy than the reactants. If I go the other way around, product to reactants, it's endothermic. They always work together. So, first question. Label, provide names for the labels 1 to 4. Okay, and I'm hoping some of you are screaming at your TV right now, going, oh, we can do that. So, number 1 is over here, and number 1 is the distance between the energy of my reactants to the top part by my activator complex, which means number 1 is my activation energy. Okay? Activation energy. Alright, we all okay with that. Number 2. Number 2 is the difference in energy between my reactants and my products, which means it's delta H. That's my enthalpy. We're all still with me? Number 3. This one's interesting because I actually haven't spoken about this. Number 1 is the activation energy when I go A plus B goes to C plus D. So this is actually the activation energy for the forward reaction when we read the reaction from left to right. If I now go from C plus D all the way up the hill to A plus B, I need to add in a lot more energy. That's what number 3 is. Number 3 is the reverse reaction activation energy. So if I want to reverse it, I need to put in more energy, which hopefully makes sense. It's like a rechargeable battery. A rechargeable battery, when we're using it as a battery and it's applying current, it's a spontaneous reaction, doesn't need a lot of help off it goes. In order for it to reverse, for it to go back to being able to supply current, you have to add energy to it. And it takes a lot of energy, so we have to plug it in and recharge it. So this is what we mean by reversible. It can go in two directions. If the one direction is exothermic, the other direction is endothermic. But what's very important to note here, number 4 here is my activated complex. Now the activated complex is the same whether I'm going forward or backwards. Doesn't make a difference. Forward, backwards, activated complex, exactly the same. Okay? No issues there. Alright, now they so we've got the same diagram. Calculate the activation energy for the forward reaction shown on the graph. So now we've got to go, okay, the activation energy is the difference from here to here. So in other words, it's the difference between the 600 and the 100. So let's write it in over here, okay? So my activation energy, which we can call EA, okay, is going to be, now I could write energy, let's not get complicated, okay? From the graph we saw that it's 600 minus 100, so it's 500. Now let's just check what units it's in. Given to me over here, kilojoules per mole. Okay, make sure you use the same units. Sometimes they don't have the per mole. It depends on the question. So use the right units. Calculate the overall enthalpy for this reaction. Enthalpy means delta H. So, as an equation, I'm going to have to take delta H, and I'm going to take the energy. We need to actually write it as an H, sorry. We're going to take the energy of the products minus the energy of the reactants. Now I know you're busy going, Tracy, why is it H and not E? Because we're looking at enthalpy. Okay, so even though we're talking about energy, enthalpy is just an our special word, and in chemistry we use H. So now we look and we go, okay, the products minus 150, the reactants 100. So that means I'm going to have to go minus 150 minus 100, and we get minus 250 kilojoules. Ooh, no, that was terrible. Kilojoules with a small k, kilojoules per mole. Okay, very exothermic, negative exothermic. Okay, so Avram,
Yes.
I'm pretty much done, but before I do a summary, do you think are there any questions?
Here's a quick one.
Yes.
Please explain to me what is meant by activated complex in simple words.
Okay, in simple words.
Yes.
Okay, the activated complex basically is, if we look, let me get to a blank page. Okay, so let's look at the water one, okay? So we had hydrogen plus oxygen. Now, hydrogen, if we do it in dot molecules, I'm sure you remember doing this when in grade 9, so that's pretty much what they look like. The activated complex happens when, as these two come along, okay, they now form a big little compound that maybe looks like that, okay? It's just, they all put together. But this is unstable. It can't stay like that. It's got so much energy. It's like when you drink energy drinks and bounce off the walls and drive your teachers mad, okay? You get so much energy, it's got to give it away. So either the activated complex has got to make the new bonds, or it's got to stay with the old ones. But it can't stay where it is. So it's temporary and it's very unstable. It's a halfway station. It's like the halfway stage before it decides what it wants to be. Yeah.
I hope
Yeah.
it answers that one. Can you take a quick one also?
Yes.
Another one. Okay. when will you do friction?
Oh, friction. We did that earlier this year. So in terms of friction, sweetie, go look back in we did it right at the beginning of the year when we did Newton's laws.
All
so
right.
it's on the website. The notes are there. The videos are there.
I wanted you to tell them actually.
Okay.
It's there, the video is there on YouTube also.
It's there on YouTube, guys. The notes are still there. and the videos are there, and we did do it. We did them in the U.
And the notes.
And the
also.
notes. Yeah, we've pretty much finished physics for the U.
Wow, unfortunately, time flies, especially when you're learning so fast and so much. Otherwise, Mindsetters, thank you for tuning in and thank you for taking your time to learn with us, Mindsetters Grade 11s. Go to curo.co.za and fill in the assessment. Your code is PS11. From us, Tracy and AB, we just want to say thank you very much. Peace.